So the topic of this video is taking a look at the energy associated with physical changes, basically heating and cooling curves. So a result of things changing state, going from solid to liquid to gas and so forth. So with a heating and cooling curve, notice the axes. The y-axis is the kinetic energy or the temperature, and the x-axis is time. So what we're taking a look at here is how the temperature changes as something moves from, notice, a solid to a liquid to a gas. Also note that there are 5 different sections. Sometimes you have diagonals, sometimes you have plateaus. So what's going on at the diagonals is very different than what's going on at plateaus. A cooling curve is just the opposite. You can see a cooling curve now starts high and goes low because we're removing energy to cool something as opposed to adding energy to heat something. So what I do to the heating curve is pretty much the opposite, equal but opposite of what's happening at the cooling curve. We're adding energy in a heating curve, we're taking energy away in a cooling curve, but the ideas that are changing and the calculations that you would need to use are exactly the same. It's just a matter of, is heat going in or is heat coming out? So let's start where the graph itself starts. So at the lowest temperature, we have a solid. So I'm going to make this my red line here. So this section A represents us increasing the temperature of the solid. So when we apply energy to an ice cube that's below 0, so it's not starting to melt yet, it's actually in a freezer that's below 0. When you start adding energy to that solid, what's going to happen is the energy is going into making the motion of the molecules increase. Now, since it's a solid, there's not a whole lot of motion. So the only motion associated with a solid is vibrational energy or vibrational motion. So as you add energy to a solid, the atoms' bonds will start to stretch, the IMFAs will start to stretch, the bond angles will start to change a little bit, they'll start to wave back and forth and so forth. But we're not breaking any bonds at this point, and that's important to know. So there's no bond breaking going on. As a result, because motion is changing, the kinetic energy is increasing, and that's obvious because we're rising along the y-axis. But what's not changing is potential energy. Potential energy is the energy of bonding. That's constant. So the potential energy is constant because we are not changing bonding. So as you add energy to the solid, the molecules vibrate more and more and more and more, so the kinetic energy goes up until we get to this point here where now the molecules have enough vibrational energy. The bonds are stretching so much, the IMFAs in this case, there are no internal bonds changing. Covalent bonds don't change, just IMFAs when you do a heating and cooling curve, when you do a state change. So at this point, you now have added enough energy that some of the IMFAs start to break. And so we cause the solid to become a liquid. And so what's happening at this point? We're breaking bonds, we're breaking IMFAs, which means our potential energy is changing. Potential energy is rising as we go from left to right on the plateau. So potential energy is stored energy. When you start breaking IMFAs, you have to put more energy into the molecules because you're making them unstable. Stable things have less energy, unstable things have more energy. When you break a bond, you're destabilizing something. So we're actually increasing the potential energy over time as we go from left to right along this plateau. But what's not changing? Since we're on the plateau, temperature is not changing, which means kinetic energy is constant. And as a result, motion is essentially constant. So we're not making the molecules vibrate anymore. We're actually vibrating at the same rate, but because the vibration is so much, we're starting to break bonds. So it's really cool when an ice cube melts. If you were to have a thermometer inside an ice cube, as it melts, you don't see the temperature change. You can see that better with boiling water. If you put a thermometer in boiling water, the temperature of boiling water stays at 100 degrees. It doesn't change. So when you're doing a state change, temperature stays constant because the energy that's being absorbed by the molecules is going into breaking IMFAs. So once we've broken enough IMFAs to convert that solid to a liquid, so along this plateau, we essentially have both states present. On the left side, there would be more solid. On the right side, there's more liquid. But until we get to the end of this plateau, you have both in existence. So there is essentially an equilibrium between the two, the solid and the liquid. If we could maintain this temperature and not add any more energy, you would see ice and liquid coexisting together. But since this is a heating curve, and over time we're constantly adding energy, we're actually melting the ice. Okay, so once we've melted the ice, now we're going to increase the temperature. This is a very thin pen. We're going to increase the temperature along the second diagonal, which doesn't come out very well. And so what we're doing here is, once again, because we're at a diagonal, hang on, I got to get a new pen. Because we're at a diagonal, we are increasing the kinetic energy once again. So the kinetic energy is going up. The potential energy as a result is constant. We are no longer breaking any IMFAs. So what's happening? So no bond breaking. But we are increasing motion. So now not only do we have vibrational motion, because we've broken some IMFAs, we also have rotational motion. So you wind up with more energy being used to make the molecules move even more. So as we increase that rotational motion and more vibrational motion and so forth, the temperature of the liquid heats up, heats up, heats up until you get to this point here, which is now the boiling point. Now we're going to take the liquid and convert it into a gas. But once again, you've guessed it, we're at a plateau. So at the plateau, once again, different things are happening. At this plateau, because it's a plateau, kinetic energy is constant. But what is changing? Potential energy. What are we doing? We're breaking IMFAs. By the time we get here, all the IMFAs will have been broken. But motion is staying constant. So at this plateau, we've got constant kinetic energy, which means we have constant motion. So the molecules aren't moving any more along here. The energy is being absorbed in order to break IMFAs. And like I said, by the time we're done here, there'll be no IMFAs left because we'll have converted everything to a gas. And remember, gases are independent. Their molecules move independently of every other molecule. So you can kind of see a pattern going on here. So notice that you cannot have a liquid beyond its boiling point. If you add energy to a liquid and convert it to a gas, then you can increase the temperature of the gas. But you can't get a liquid, for example, water. Temperature of liquid water can't go above 100 degrees Celsius no matter how much you try. It's the steam above the water that can get hotter. So when you take the lid off a pot of boiling water, it's not the water that can burn you worse. A steam burn is going to burn you much worse than a hot water burn, because a hot water burn's only 100 degrees max, whereas steam can be minimum of 100 going higher. So finally we come to this third diagonal. We are in the gaseous state, so we technically could continue to add energy and keep it as a gas, get those molecules moving more and more and more, increase the pressure, increase the volume, all that kind of stuff that you learned in the last unit with gases. But once again, let's keep everything consistent. So now all the IMFAs are broken. Potential energy is constant because we're not changing any IMFAs. And we never, again, on a heating curve, you never break covalent bonds. But what is changing? The kinetic energy is going up. And so now we've got a third type of motion. Not only do we have vibrational and rotational, but you have the motion of position, which is called translational motion. So because the gas molecules are independent and can move all over the place, you wind up with vibrational, rotational, and translational motion. Okay, so that's a heating and cooling curve qualitatively. I'm going to stop here, but make a second video because we have to talk about how you actually calculate numbers. So this is the qualitative stuff that's going on, but now we've got to look at the quantitative stuff. So once again, I'm going to pause this or stop this, take some notes if you have not already, and then when the next video starts, we'll be talking about calculating the energies associated with these changes.